Some of you may have heard that time is relative, as stated by the amazing Albert Einstein. His theory can be divided into two parts, special relativity and general relativity. Special relativity argues that the state of one object can only be measured relative to another object. Can you tell whether a baseball is moving through space? By itself, there is no way to tell. Having a separate object, like a basketball, allows you to measure the position of the baseball relative to the basketball, and thus answer the question. You might ask, how can time be relative then? It's not like any one thing is moving faster through time than another. And you'd be right. The key is in the speed of light. Since we're all moving through time at a rate of 1 second per second, the times at which we observe events depends on how long it takes for light to transfer the information from the event to our eyes. On Earth, we're all pretty slow relative to light, so it's hard to observe this phenomenon as every event happens at the same time for everyone near the event. So, let's imagine that the sun explodes at t equals 0. At about 8 minutes, the information reaches Earth, and it's lights out for everyone. For a Martian, the information reaches them in about 13 minutes. Special relativity suggests that this also applies to a situation where two objects start at the same distance from an event, but one of them starts moving at a significant speed. So Einstein established a relationship between time and space, but things start to bend when the reference frames are not inertial. This is where general relativity becomes useful. Einstein theorized that objects bend the fabric of space-time, and as an object approaches this area of warped space-time, it begins spiraling inwards. This also is another representation for gravity. The warping of space-time also affects light, so by playing with general relativity, we can get creepy yet fascinating results. Take the black hole for instance. It has an immense mass, which greatly bends space-time. But if an object were to fall into the black hole, its trajectory through space-time would change. From the outside, it appears as if the object entering the black hole slows down to a complete stop, because it has stopped moving relative to them in the time dimension. Inversely, the object inside the hole would see everything speed up, to the point where they see the universe age by billions of years each nanosecond.